Welcome to the wonderful world of physics. This is section 10.3, rotational inertia. We have seen so far in chapter 10 that there are rotational analogies to linear concepts that we learned back in chapter 2. For example, acceleration, its rotational analogy is angular acceleration. Same for linear velocity, we got angular velocity, designated by omega. We have x, and that's theta for distance or displacement. Now we're talking about an angle. And we've seen that force, its analogy is torque. Now, we have Newton's second law, F equals ma, which means that the force that you apply to something is equal to its mass times acceleration, and we can think of mass as a body's inertia, meaning its resistance to change in motion. The more mass something has, the more force you're going to need to get a given acceleration. And so the question right now is there some corresponding analogy to F equals ma? And we can imagine it might go something like this. If torque is the analogy to force, and alpha is analogous to A, acceleration, might we have an equation that says torque equals something times alpha? That's something that would take the places of mass, meaning the body's rotational inertia. So we'll just leave it like this, thinking that maybe there is an equation that torque is equal to some mystery thing, I'll call it rotational inertia times alpha. So the question, what quantity is resistant to change in rotational motion? And to answer that, I want to consider a simple setup, a mass that's on a rod. So it's on a rod, there's the pivot point on the left, the rod is of mass r, and we apply a force, a perpendicular force, to that mass so as to accelerate it. So we get force equals mass times its acceleration. Now, since it's going to be moved around in a circle, we can call that the tangential acceleration. We know from a previous lesson that tangential acceleration is alpha times r, so we'll make that substitution. Now, torque is equal to rf times sine of theta. Here I've neglected the sine theta because it's perpendicular, it's the sine of 90 degrees, so we'll just say torque is equal to the length of the rod, or the radius, that lever arm, times the force that's applied. And what we get is torque is equal to r times, and this F, I'm going to do m alpha r, so we get torque is r times m alpha r. Clean this up and we get torque equals mr squared times alpha. And remember that equation at the top of the page, torque equals what times alpha? And there we've solved the mystery. It is mass times r squared that takes the place of mass in the rotational formulas. So this is the quantity, mr squared, for that single mass that is resistant to change in acceleration. And we're going to call it, just as I called it earlier in this video, rotational inertia. It's also known as the moment of inertia, so either phrase works. And we use the capital letter I for it. Its units, you can see that it's kilograms meters per second squared. And notice that in linearly, F equals ma, it's just the mass of an object that resists a force. With rotational motion, it's a bit more complicated. It's not just the mass, but it's the distribution of that mass. And specifically, it has to do with where the mass is located relative to the axis of rotation. So for torque, we use that Greek letter tau equals I times alpha. It applies to extended objects as well. When we're calculating the rotational inertia of an extended object, we're just going to say that rotational inertia is the sum of every mass times r squared. And in this case, r is the distance of that mass to the axis of rotation. Now, I'd like you to read example 10.4 in the book. I'm not going to go over it with you, so you can pause the video here and I'll wait for you. Okay, I'm done waiting. Here we go. You've hopefully looked through example 10.4 in the book. Now I want to add to it. For example 10.4, what if the axis of rotation were in the center of the dumbbell? So this is just a follow-up question to give you more practice here. Well, in this case, you would have moment of inertia, and we're going to add the moment of inertia of every individual part. Again, we're assuming that the rod is massless because we don't yet know how to deal with a continuous body. We're just dealing with the weights on the end. So we have the first weight. It's 0.64 kilograms times, and it is 0.425 meters away from the axis of rotation, squared, plus the other weight is the same thing, 0.64 times 0.425 meters squared. And what we get is 0.2312 kilogram meters squared. Remember what we're calculating. We're looking at moment of inertia, otherwise known as rotational inertia, and it is the body's ability to resist being turned by a torque. And so this dumbbell has a lower moment of inertia by making its axis of rotation in the center. Which leads to the next question. Where should the axis be to minimize moment of inertia? Now this isn't in the book, but it's a neat thing to be able to do. I use that word minimize, and hopefully that brings up memories of calculus and doing derivatives, setting them equal to 0. That's what we're going to do. In general, let's look at the picture. There's the first weight, the second weight, and it has a length of L. And X is going to be where, hypothetically, we're going to put our, the position where we're going to put the rotational axis. So we can say that for the first weight, it is m times x squared, because here's the axis, so it's m times x squared, plus the second weight is a distance of L minus x, and so that's going to be its mass times L minus x squared. I'm going to clean that up algebraically. I'm actually setting it up to do a derivative. So the moment of inertia is mass times 2x squared plus L squared minus 2Lx. Let's minimize I by taking the derivative with respect to x and setting it to 0. So the m goes away. We have 2x squared. That becomes 4x. This L squared is constant. It goes away. 2Lx becomes 2L, and we're left with 4x minus 2L. We solve that, setting it equal to 0, and we get x equals 1/2 L. So right in the middle is what where minimizes the moment of inertia. Now, we got the middle, and actually, what if these masses, we could further push this and say, what if the masses were different from each other? What we would find is that it's actually the center of the mass. If the axis is at the center of mass, that's what will minimize it. So if you want to play with this calculus, you could set up a problem where this mass on the left is maybe 3m and the mass on the right is m, and work through the calculus, and you'll get a different position for a minimized rotational inertia. So you can see how that works. Now, we set the derivative equals to 0. Remember from calculus, that could be a minimum, it could be a maximum. And one thing to think about is, how do we know that we've just found the minimum and it relates to the second derivative? Okay, now let's look at a continuous distribution of matter. So we get beyond simply looking at discrete masses like the two weights on the end of a dumbbell. What about the rod that we neglected in the previous problem? What about if it's a sphere? What about if it's a cylinder, a disk? So a continuous distribution of matter. We have moment of inertia is the sum of every m times r squared. And we're going to take very tiny mass elements, because that rod in the previous problem can be thought of as many, many billions of little masses. And all of them contribute a little tiny mr squared. So this sum as we take m going towards infinitesimally small, becomes the integral r squared dm. The next few examples, very often through this class I'm just going to have you look at the examples on your own, as I did with example 10.4, but it's useful in the next three examples for me to actually talk you through them. So let's do it. Example 10.5, the rotational inertia of a rod. Example 10.5 says, find the rotational inertia of a uniform narrow rod of mass m and length L about an axis through its center and perpendicular to the rod. All right, so we've got this picture right here. Notice what I've drawn in the diagram. It has a length of L. And the axis of rotation, I draw it right here with a dotted line. So this thing is going to spin around. We're going to make the axis of rotation in problems like this, x equals 0. And so on one end, we're going to have x equals negative L over 2. On the other end, x equals L over 2. As you'll see as we move down the page, those will be our limits of integration from negative L over 2 to L over 2. We're going to break this rod down into many, many mass elements of mass dm. They have a length of dx, and they are at a position of x. And just as we did a few chapters ago when we were integrating to find the center of mass, we don't want to integrate with respect to dm. We want to integrate with respect to something spatial. So we're going to relate dx to dm and get rid of that dm in the integral. So here's what we'll do. We'll recognize that the length of this mass element divided by the length of the rod is equal to the mass of the elements divided by the mass of the rod. So we can say dx over L equals dm over m. This will be your first step in any type of problem like this, where we want to find something spatial that relates to dm. So we solve for dm, and we get mass over length times dx. Now we can plug that into the integral. Moment of inertia is integral of r squared dm. And notice my limits of integration from negative L over 2 to L over 2. Since we're looking in the x direction, anything that is r in the integral, lowercase r, we're going to turn into x. So r squared magically becomes x squared. And dm becomes m over L times dx. From here, you just follow that integral through. M over L goes out to the side. You can see this integral here, and we end up with 1/12 ml squared. So that is the moment of inertia of a narrow rod of uniform length, uniform mass throughout its length, 1/12 mass times its length squared. Let's do another problem like that. What if the rod is rotated not about its center, but an axis that's on its end point, such as in this picture? Well, the one thing that changes is your limits of integration. We're going to draw the axis, and wherever the axis is, we're going to call it x equals 0. Then the limits of integration are going to go from 0 to L. Everything else I did is the same, so I equals, it's going to be the same integral that I had right here, but limits of integration from 0 to L. And so you get 1/3 ml squared. Now, when we rotated the rod through its center, it was 1/12 ml squared. Now, when we rotate it about its endpoint, it's 1/3 ml squared, which means it's 4 times greater than when we rotated it about its center. Remember, we saw in a previous example that it's going to be, something is going to have the lowest moment of inertia when you rotate it about its center of mass. Well, here we see we're as far from the center of mass as we can get without leaving the object, and it's 4 times greater. You can feel this for yourself. If you take a long pole, maybe a broom will work just fine, a hockey stick, baseball bat, something like that. And first, mimic this first example where you hold it in the center and just twist it in your wrist, kind of like I'm doing with this pen right here. Just twist it, and then hold it on the end and try to twist it. And it's more difficult doing it like that. Okay, next example. Example 10.6 is of a ring. And please make sure you read the example in the book. The example's in the book, but this is for a thin ring, and it's important to note this is a thin ring of radius r and mass m rotated about the ring's axis. So it's a wheel that's spinning. We're going to take this ring and divide it into little mass elements, dm. One thing that's going to make this very easy is that r is equal to the radius of the ring, meaning every mass element is an equal distance away from the center. So we take our integral, I equals r integral of r squared dm. Usually when we do problems like this, trying to find the moment of inertia, we have to set up some ratio where we relate dm to something spatial. In this case, it's actually simpler not to. So we have r squared, we replace that with the constant r squared. R squared goes out to the side, and the simplest integral you can do, the integral of dm, and that is just the sum of all the mass elements, it's just the mass of the ring. We get mr squared. This is the same result as if you think about a simple mass on a rod of length r. This is how I started this lecture, actually. And it's pivoting, and we got the same result. Its moment of inertia is mr squared. So it doesn't matter that it's shaped in a circle. The point is that all of the mass is a distance r from the center. So mathematically, it turns out to be just like this, that if it's concentrated right there in the mass. Also, I want you to notice, we never talked about the height of the ring, how tall, how high it comes out of the paper. The ring's height doesn't matter because that doesn't affect how it's distributed from the center. So this could be a cylinder as well. So this equation works for a ring as well as a cylinder. Okay, we're going to use the result from example 10.6 in example 10.7. So example 10.7 is a disk of radius r and mass m with uniform density. Find the rotational inertia, once again about an axis, through its center and parallel to the disk. So my pen is the axis of rotation, and it's going to spin around that pen. We're going to divide this disk into many rings of mass dm, like tree rings on a tree stump. Now in example 10.6, we learned that for a thin ring, moment of inertia is mr squared, and we're going to use that result, so we don't have to repeat that work. However, the big M, where it was the big M for a ring, now each of those rings just has a mass of little dm. So we can say the moment of inertia of each ring is r squared. Now that's little r squared because they're all different distances from the center, times dm. The total of all the rings is just going to be the sum of all the r squareds dm. So it's going to be the sum, but sum is an integral, of r squared dm, the sum of all of these, and integrated from 0 to r. Now, we once again don't want to integrate with respect to dm, and so let's relate r and dm. What we can do, get a little creative here, is imagine taking this ring and unwinding it so that it makes a rectangle. That rectangle, let's think about its area. It has a width of dr, so this little width is dr, and it has a length of whatever the circumference of that ring was, so 2 pi r. So we can say the area of one of those rings is the area of that rectangle, which is 2 pi r times dr. With that in mind, we'll say that the area of one of those rings divided by the area of the entire disk is equal to the mass of the ring divided by the mass of the disk. So let's plug everything in. The ring area is 2 pi r dr. The disk area is the area of the circle, pi times big R squared. Ring mass is dm, disk mass is big M. We can solve for dm. I've got it right here. You notice pi divides out from numerator and denominator. And what I'm going to do next is plug that into the integral. So moment of inertia is the integral from 0 to big R of r squared dm. And let's make this substitution. Take this, plug it in there, and you should get r squared times 2r m dr over big R squared. Now this r squared and this r can be combined to make r cubed. The 2 and the m and the over big R squared can go out to the side. And we're left with this simplified integral, 2m over r squared times the integral of r cubed dr. You solve that integral, and you get 1/2 mr squared. The moment of inertia, then, for a solid disk is 1/2 mr squared. Remember that for a ring, it was mr squared. So the ring, when all the mass is distributed as far away from the center, from the axis as possible, it has a greater moment of inertia. With a solid disk, like in this example, smaller moment of inertia because some of the mass is right at the center, so it doesn't contribute much. Some of it is around a middle radius, and some of it is at the very edge, so it's spread out over the disk, so it's going to have less moment of inertia. Table 10.2 is very important. It actually shows these results. And so you can refer to 10.2 in your studies, in your homework, with your tests. I know the print is probably too small to see on your screen, but what it shows is some of these we have just arrived. Thin rod rotated about its center, 1/12 ml squared. We found that. Thin rod rotated about its end, 1/3 ml squared. We did that. Thin ring or hollow cylinder about its axis, 1 mr squared. We did that. Disk or solid cylinder. Remember, it doesn't matter. Just like with the ring, it didn't matter how long it was along that axis of rotation, so it can be a cylinder. Also for a disk or a solid cylinder, 1/2 mr squared. And we just solved for that. Other ones you'll find in the book are a solid sphere and a hollow sphere, a flat plane about a perpendicular axis, and a flat plane about its central axis. If you look at flat plane about its central axis, it's 1/12 ma squared, and so this is the length A right here. This is the length B. Notice it doesn't matter how tall B is. Doesn't matter at all because that doesn't affect how it's distributed away from the axis of rotation. Now, if B doesn't matter, imagine squishing it down, making B very small. So this is just, well, if you squish it down, it's just a rod of length A. 1/12 ma squared. And that's exactly like this one here, a thin rod about its center, 1/12 ml squared. So, table 10.2, use that when you need it. Now sometimes it's a bit more difficult to integrate, or sometimes maybe not more difficult, but if we can find a shortcut, it's nice to have one. So consider the moment of inertia about an axis through a body's center of mass, and we'll call that I center of mass. I want to introduce you to the parallel axis theorem, which says that the moment of inertia through any axis, through any parallel axis, is equal to the moment of inertia of an axis through the center of mass plus md squared, where d is the distance from the axis to the center of mass axis. I should have said to the center of mass axis. Now, let me give you an example of this. The moment of inertia of a thin rod, excuse me, let me move the camera here. Okay, the moment of inertia of a thin rod where its axis it's going through its end. Now, you just saw the answer in the table, and we solved for this in an earlier example, but let's use the parallel axis theorem. Let's say we don't know that the answer is 1/3 ml squared. Let's say that all we know is the moment of inertia if it's rotated through its center of mass. That's 1/12 ml squared. Well, the parallel axis theorem says that we can say the moment of inertia if it's rotated through its end is the moment of inertia if it's rotated through the center of mass plus md squared. Moment of inertia through the center of mass is 1/12 ml squared plus mass, the distance. We're looking at the distance between the true axis and the center of mass. That's L over 2. And we're going to square it. So it becomes 1/12 ml squared plus 1/4 ml squared, and that's 1/3 ml squared. And that's exactly the result that we've seen before. Another example, let's say we have a sphere and we want to, as if we're palming the ball, we want to grab it right here and rotate along its surface. And the integration of that would be very difficult to do, but parallel axis theorem will save the day. So here's the axis, and we're going to relate it to the axis being through the center of mass. And this ball has a radius of r. So the moment of inertia, as we rotate it about that axis on the surface, is the moment of inertia with the center of mass plus md squared. Well, for a solid sphere, the moment of inertia, if it's rotated through the center of mass, is 2/5 mr squared. You can get that from the table we looked at before. Plus mass times, and in this case, distance is the radius of the ball, r squared. So we have 2/5 mr squared plus mr squared, and that's 7/5 mr squared. At this point, I would like for you to do example 10.8 in the book. And you can pause the video, and I'll be here for you. Okay, 2 problems I'd like to do as we close this section. Adjust my camera here. Okay, the first, this is a problem in the back of the book, is problem number 52. It says a uniform rectangular flat plane has mass m and dimensions a by b. Use the parallel axis theorem in conjunction with table 10.2 to show that its rotational inertia about the side of length b is 1/3 ma squared. Okay, so we'll draw a picture. And here's the axis, the center of mass. And I draw that because this is what we're going to find in table 10.2. But now it's being rotated about side B. So the moment of inertia as it's rotated about side B is moment of inertia about the center of mass plus md squared. Well, we can look up in table 10.2, and the moment of inertia as it's rotated through the central axis is 1/12 ma squared. Plus, we're going to say mass times this distance, and the distance between these two axes is a over 2, so we'll say a over 2 squared. So we've got 1/12 ma squared plus 1/4 ma squared, and that becomes 1/3 ma squared. Now you can go back and see, I'm going back to the previous page, it's actually very much like this problem here on the previous page, moment of inertia of a thin rod about its end. Finally, problem number 59. Let's do it. Problem number 59. I'm going to save this for another video. So that'll be it, and stay tuned for another video that covers problem number 59.